Hello friends, welcome back to another video. So, if you might remember, I think a year ago or maybe more, I showed the general solution of a Gaussian integral, such as the one here on the screen. So yeah, I'll put a link to that video. And now I was wondering, since this is an expression like a sequence, right? Like we can think of the sequence, in. Can we sum it? Can we do something interesting with it? Obviously, this will blow up. Well, will it blow up? It actually won't, will it? So, first of all, there is an identity that I need to prove. So this 2n minus 1 double factorial, remember that's 2n minus 1, 2n minus 3, and so on up until 1. And so we can see that that's just 2n minus 1 factorial without 2n minus 2, 2n minus 4. And so how long does that keep going? It keeps going until 2n minus 2n minus 2. Right? Because yeah, we need to lose 2. This is just 2, of course. So we can pull out a 2. We can pull out, well, many 2's actually. So we're left with 2n minus 1 factorial. And so how many 2's will I pull out? So here I have n minus 1, n minus 2, and then it goes to n minus n plus 1, right? Times all of these guys times 2. So we're going from n minus 1 to 1, so that's going to be 2 to the n minus 1. And then we're just left with n minus 1 factorial, right? So n minus 1 factorial. And one more time, we can simplify this to 2n factorial over 2n n factorial, just including the newest term. And there we go. So this is nice, I guess. So then this means that in is also square root pi 2, oh, well, it's 4 to the n factorial over 2n factorial. Now, honestly, maybe I should have thought about if this thing itself can limit to anything. And naively, I would guess that yes. I know that the factorial grows about as much as e to the n, I believe. So, or the square root of the factorial, but this doesn't matter for our analysis. What I wanted to show is a use of this identity when trying to find the Fourier transform of e to the minus x squared. So of the Gaussian, right? So we call, maybe like I'll write it like this. So the g of x, g for Gaussian, is gonna be e to the minus ex squared. So of course, like I could add a parameter a, you know, like it could be e to the minus ax squared. But you can see that this is just up to change of variables in x. So I'm not going to bother with this. So this is going to be my g of x. And I'm going to be wondering what the Fourier transform of g, maybe evaluated at xi, is going to be. And so this is, of course, by definition, from minus infinity to infinity, e to the minus, well, okay, I can write g of x, and e to the minus I xi dx, I xi x dx. This is the definition of the Fourier transform. Well, this doesn't really look like what we have, does it? Well, that's where the fun comes in. So let's think of this Sn. It's going to be a series rather. So it's going to be an infinite series where, it's not of n. Is it going to be of x or just s? Yeah, I guess just s. So n will be ranging from 0. From 0 to infinity. And we're going to sum over these in integrals. And then what else are we going to use? we are gonna use, we want to divide it by n factorial. Yeah, we want it to be of xi, s of xi. And then we'll have I xi to the nth power. It might look random now, but let's just see what it gives us. Okay, so it's going to give us two things, and the two things that it gives us is what we want to equate. So first I'll show that this is indeed the Fourier transform of G. So I'm going to write the integral in as an integral. All right, so I'm going to write this part. Sorry, this is not n factorial, this is going to be 2n factorial. I'm just making this up, by the way, so I didn't see this anywhere. It just looked fun. So yeah, here's the integral. In is x to the 2n e to the minus x squared. Okay, and then we've got this 2n factorial, and we've got I xi to the nth power. Yeah, I want this to the 2nth power as well. dx. Okay. And I can interchange the integral and the sum because we know that all of these integrals converge. So there's no problem. Perhaps this is why it would be nice to check that the individual terms are bounded, right? So that I could really interchange, but let's pretend they are. You know that I'm a physicist. So we got this integral. I can leave e to the minus x squared outside. And then n equals 0 to infinity. And now we've got, look at that, I xi x to the 2n over 2n factorial. Well, I guess I don't need to do it this way, do I? Yeah, I do. I want to do it this way. So I'll just write this minus 1 to the n. And now you guys should be recognizing the cosine, right? So this is the identity of the cosine, you know, the cosine xi of x, the sum expansion, the series expansion of cosine x. So this would be like 1 minus xi x squared over 2 plus and so on. So this is equal to just minus infinity to infinity e to the minus x squared cosine xi x dx. And now you might be wondering, well, how is this the Fourier transform? Well, I'd like to remind you that this would actually be the real part of the Fourier transform. As you can see, the real part of e to the minus I xi x is cosine xi x. It will be the real part of the Fourier transform of G. Maybe let's just call this G xi, G hat xi. So this would be the real part of G hat xi. But you might notice that the imaginary part of G hat xi is 0, since e to the minus x squared sine xi x, this will change sign to minus when x is negative, right? So this is odd, this is even. And so because of that, the two intervals cancel, the two half intervals of the real line cancel. So because of this is just G hat of xi. Okay, so there you go. So S of xi, this series, is the Fourier transform of the Gaussian by identity. Now, on the other hand, we need to evaluate the series. So this was step 1, showing that this series is G hat of xi. And then step 2 is evaluating the series, because we don't want to evaluate this integral. It would involve completing the square, right? I'm just trying to think of a use for this, right? This guy would involve completing the square, and for xi imaginary, it you'd have to, be pretty rigorous. You'd have to do like a contour integral or something. I've even seen, yeah, I've seen weird shit here. So I think it's easier to just evaluate this. So S of psi, now I'm also going to write this, but I'm going to write what IN is explicitly. So let me just copy this because I'm extremely lazy. So there we go. We've got square root pi 2n factorial 4 to the n over n factorial. I guess square root pi can be outside the sum. N goes from 0 to infinity, and now we've got to include the rest. So I psi 2n over 2n factorial. Of course, this nicely cancels. I wouldn't have been doing this if it didn't. And it gives us the square root pi sum n equals 0 to infinity of I psi, minus psi squared over 4 to the nth power over n factorial. And look at that, all of you who have seen the Fourier transform of the Gaussian before know that this will in fact be square root pi, so yeah, of course this is the exponential function, e to the minus psi squared over 4. Look at that. That's what we're supposed to get. I don't really remember if there is a square root pi here. I guess there is. It's pretty ugly. I guess that comes from the definition of the Fourier transform. Yeah, because there's going to be 1 over square root pi. So that has to go away later. So basically we've just proven that the Fourier transform of G evaluated in psi is square root pi e to the minus psi squared over 4. This would of course mean that the Fourier transform of G evaluated at 2 psi is square root pi e to the minus psi squared, and this is equal to square root pi G of psi. So yeah, the G being the original function, right? So this is I guess a nice little connection. So if we did another Fourier transform, we'd get another factor of pi. If we did the inverse Fourier transform, we'd lose the factor of pi because, the inverse divides by pi. Yep, that's pretty nice. I think, yeah, that's it. I need to learn how to end my videos better. But yeah, I think this is a fantastic result because, like I said, otherwise, when psi is imaginary, you'd have to go through some tricks. But here, there are no tricks to go through, and the reason is because the exponential function, the series version is convergent without any constraints, right? So it can converge anywhere in C. Yep. There you go. Hope you guys enjoyed it, and see you next time. Bye-bye.